Now, here's Peggy Small with the weekend weather.
Thank you, Bob. Well, you can get just about anything you want this weekend. How about a little rain? Mother-in-law coming? A little hail, perhaps. All you need are a few proper clouds, your airplane, a special silver iodide nuclei generator, and a little information, which I'll give you. What we're talking about is seeding cold cumulus clouds, clouds whose tops extend above the freezing level. You'll find either type A cumulus, a cloud in a low wind field, type B cumulus, a cloud in a wind shear where the wind velocity increases with altitude, or type C cloud, where the wind velocity actually decreases with the altitude. Now, the idea is to get silver iodide from these nuclei generators into the part of the cloud where it'll do the most good. A sturdy aircraft, multi or single engine, capable of sustained operation at 25,000 feet is just the ticket. Carry supplemental oxygen and be certain your plane has dual navigation communication gear. Dual automatic direction finders are handy items. So is an instrument landing system and a transponder. An instantaneous rate of climb meter is also useful, and make sure the gyro horizon and gyro compass are functioning properly. So that's the plane, and here's what you do with it. Based on the most recent meteorological predictions, anticipate the cumulus cloud growth through the freezing level in the target area. And time your takeoff so that you arrive on station at the optimum point of cloud development. It's better to reach the target cloud just as it's growing the most rapidly. Only clouds that are growing can be successfully seeded. Old clouds just collapse quickly. A growing type A cumulus will have a hard white top billowing upward. Find a white-topped cloud with a diameter of 1 mile or more, the minimum size for seeding. Seed tall clouds rather than flat clouds. Locate the -3 to -4 degree centigrade level, optimum for silver iodide nuclei. Set trim and power for level flight. While well away from the cloud, select a path which will lead you clear of other clouds. A good approach speed is 1 1/2 times the stall speed of the aircraft. Don't nose up as you approach the cloud. Trust your instruments and continue to fly attitude. Immediately outside the cloud, there's a downdraft, which quickly neutralizes. Turbulence increases until you get the hard upward jolt of the main updraft of smooth air. If the updraft holds for a few seconds, fire around. The windscreen will pick up water. If water accumulation in the updraft lasts several seconds, fire another round. When exiting the cloud, you'll again hit the downdraft. A 90-degree, 270-degree maneuver will get you around to watch the seeded tower develop. Usually, the volume of tower above the freezing level doubles within 5 minutes of seeding. If little growth occurs, seed the cloud tower again, unless it's dissipating or breaking off. But new towers or nearby clouds can be seeded immediately. By seeding rapidly growing new towers around a central mass, a single coherent cloud forms, and lots more precipitation occurs. Seeding an already vigorously growing cloud or seating at levels above -7 degrees centigrade can produce a cumulonimbus. They're bad clouds. And remember, don't seat any downdrafts either, because the silver iodide is just wasted. Seating the B, or wind shear cloud, is just a little different than seating the A cloud. Rather than seating the rising core, you seed the up shear towers. Where multiple towers exist, seed the most upwind tower of good seating height. Again, look for hard white, contrasty tops. To avoid embarrassment, enter the turret only at right angles to the wind shear. After seeding, you'll notice new towers developing just upwind from those you've just seeded. Frequently, several new towers will develop within 5 minutes after the last seeding. Try to seed each new tower just as it reaches seeding level. Now, a third cloud type is a strange one, a monsoon cloud. The cloud leans upwind because the ground winds are stronger than the upper winds. The procedure is just the opposite from seeding a B cloud. Seed the most downwind tower that shows promise. With this basic difference, B and C clouds behave almost the same. Another technique is used when towers do not extend too far above the -4 degree level. These clouds can be seeded from the top. It's less precise and a little less effective, but it works. The whole schmear so far has been to get precipitation. Now, how to get rid of it. Let's say you have a developing cumulus congestus you want to get rid of. Seed the cloud in the updraft with several rounds, one every 3 seconds. The rapid growth causes the tops to break off and blow away. The base collapses and usually doesn't regenerate, and the precipitation stops. Isn't it fun to fool with Mother Nature?
Hi, it's a pleasure for me to be back with you folks again, and to even see some of the ones we'd worked with over the years. Not to mention Marie, and David, and Randolph. Jack. Jack was involved deeply with this program. He was overseas for about a half a year at one time and another. But the question is,
I'm sorry.
no importa.
There we go.
Thanks. The question is, when you're dealing with something the size of the weather on a semi-continental scale, you have to find some physical trickery to permit you to make the changes necessary. The story is developed from the physical chemistry of the late 19th century and to some extent from the 18th century. Proper water in a refrigerator tray will freeze. It won't freeze if it's real clean. It has to have something to give it a little boost towards freezing. a nucleus and some insoluble material. Most any insoluble material works, but the ones that have the closest physical structure to ice work the best of all. And if the intermolecular misfit is just about perfect, it'll work at the freezing level, at the freezing temperature of 0 degrees. That's not the proper name for it. That's the melting temperature. Ice melts at 0 degrees. It freezes in absolutely pure water that doesn't have particles of dirt and stuff in it. It'll go to 100 and some odd degrees below zero before it freezes. And then when it does that, it turns into a form of glass, which is quite different from ordinary ices. So the trick in modifying the weather this way is to find a handy means of causing the water in the cloud to freeze. When the water freezes, it gives off heat. The molecules are no longer free to move about. They are constrained to be in one position, and all of the kinetic energy that the molecules had to begin with is released in the form of sensible heat. That warms the air around the cloud, around the particles of water that are freezing. And it also reduces the vapor pressure of the water so that more water will be attracted to those drops. Now, if we go ahead a little bit, we'll try to cover it.
Yes.
Yeah, please.
This was a perfect one.
Okay, here's a picture of the world taken from a distance away in space. This is South America here. The dark spots are the ocean water that you can see from up above, and the light-colored spots are clouds. This is really a map of where the air is rising, because as air rises, it expands on cooling, and the water then will condense on whatever particles of dust and dirt are in the air. If we had an absolutely pure atmosphere, we'd never have a cloud. The water would just accumulate on everything on the surface, and that'd be the end of it. But anyway, we can see here there's great bands of clouds are forming around the equator, and those are opportunities for changing the weather. Next, please. This is a cloud over the Great Plains. The area beneath the cloud is quite hazy from the particles of dust and dirt that are entrained in the uplifting air. And as they go up, water condenses on them, and that releases heat, and the part grows and it forms a nice cloud. This one was taken over central Utah about half a century ago. Next, please. If we looked at a cloud with a big magnifying glass and we could get our heads in and see it, we would find that the droplets are about the same size, and they're separated by a large distance from the other drops. collision between the drops could take place if they were a different size or a different mass. But in a cloud that first starts to form, this doesn't happen. Next, please. If the drops are the same size, they fall at about the same speed, held back by nothing more than air resistance. If the droplets are a different size, the bigger drops will fall faster and intercept the little drops. The little drops are pushed by the air from around the sides, and they enter the bigger drops on the side, including on the back. So the opportunity you've got here to change things is to change the size of the drops. We can do that by this sort of a mechanism. We make a smoke that picks up water vapor, and water vapor then condenses on it. Next, please. This type of nuclei is called hygroscopic. It dries the air around the piece, and this causes the smaller drops near it to evaporate and deposit it on their moisture on the bigger drops. This is called the Matthew principle in the Bible. From him that hath shall be given, and to him that hath not, he's lucky to have what he's got. That's a very end of the statement. Next, please. A 20-gallon barrel filled with a compound which, when it burns, gives off sodium oxide, which changes to sodium hydroxide and takes up a lot of moisture out of the air. This trick has been used for centuries in making screening smokes. We worked on that for a long time and perfected it even to the point of developing screening smokes that gave off heat while they were growing, which would permit the use of these smokes to obfuscate infrared detectors. Here's a parachute. We dropped this out of a Cessna 205, and it caught fire after a while. Burned very nicely. Next, please. This same principle was used up at Arcata. We have some of these barrels next to the runway, and they're starting to burn there. Please. After 15 minutes to a half hour, you can still make out the runway, but these burning smoke pots have pretty well fogged it in. Another 20 minutes and the airport was completely IFR. It took a lot of arguing to get the FAA to let us do this. Next, please. There is the stratus that's formed on these flares. The flares are underneath the rising part here, and this is a trough that's been made by the downwash of an airplane flying through at the top of it. Next, please. Then, if you use large enough drops and enough of them, and you sprinkle them out over an area that's covered with fog, the droplets you spray will absorb the fog, the vapor from around the fog drops, and it'll make bigger things which will fall. Now here's the Arcade Airport, and it's now clear enough to permit instrument landing, ordinary landings without instruments. We worked it there for about 5 years, and we got so that we could, with about a 20-minute warning, clear an airport that was 0-0 to permit non-instrument landings. This was used to aid the Marines at Quezon, where they had the misfortune to select a site on the top of a hill where the breeze was continually supplying them with water vapor, and it was used there for a long time until the Marines got their act together and pushed the people off to the northeast or northwest. Next, please. Another stunt we used makes a lousy picture, but this is a great big helicopter, the largest one the Army had, and this is the runway that's in the hangar that's just been cleared off by having the helicopter push the air down. When the air gets pushed down, it warms and the droplets evaporate. It makes it a very good way of clearing off an airport. This has been used repeatedly by commercial airliners since then. Next, please. What forms the clouds take depends on the atmospheric conditions. This is over the Philippine Islands. We're having a terrible drought because the cloud growth has been limited to a temperature inversion that's only a couple of thousand feet off the deck, and the clouds can't grow through it enough to rain. So they had a terrible drought on their hands, and one of the Navy officers, a commander, Jorgensen, told them that east we could clear this off and make it rain. Well, it couldn't. But we flew around in it for a couple of days and decided that if we took this stuff out of the air, these contaminants, it might be able to get good enough clouds to form that you could expect rain. So what we did was we sent him a message to the President of the Republic and asked for an audience with him and explained that we wanted the burning of sugarcane refuse to stop all over the archipelago. Well, every year they burn all the sugarcane leaves to get rid of them, and this makes a very hygroscopic smoke. So they, after the word got out past that we should stop the smoke, why, this haze disappeared almost the next day. And then it began to rain again because the clouds could grow right through this temperature inversion on the top. Next, please. Yeah. Here is a freezing nucleus on a microscope slide that's causing an ice crystal to grow around the central part. The central part being a bit of silver iodide smoke. And you can see that well, you can't see it very well, but the dew on this microscope slide has been evaporated because the water vapor has all migrated to the nucleus. Next, please. The story now becomes one of leaving the laboratory and going out into the field. Dr. Sheldon Elliott took a Navy jet and went for a ride with him, and they flew through this cloud coming out towards us. They did a turn and went away, and they dropped a pyrotechnic device in the cloud. This was over the Panamint Mountains, where it seldom if ever rains. And this little cloud grew into a rather impressive one. The idea of making nucleants by pyrotechnics was started by two chemists here, Laura Burkhardt and William Finnegan. They made a number of compounds that would produce the smoke of any characteristics you wanted. So I got them started on making silver iodide smoke, but they worked on it. We went off for a couple of years and came back, and nothing had been done with this. And since the subject seemed ripe for the Presidential Commission on Weather Modification, this is in 57, they'd presented a big study on it and found that they really couldn't do much because they didn't have a means of making the nucleant materials. Well, no place else in the country could have done it but this place, because here we had chemists who understood how to make pyrotechnics, and we had aviators who weren't afraid to drop the things, and a number of scientists who were just looking for something interesting to do. Next, please. What was developed was the catalyst generators. We had the people at Crane, Indiana, cast them up for us. This fits in a cartridge. Cartridge fits in a photo flash, thank you, dispenser. And there's a little igniter up here and a first fire mixture which catches fire and then burns. These, and you can use different properties of material. This last one was selected so it would burn up all the rest of the remains, so nobody would blame us for it. Next, please. Here's how you see the cloud, and you saw in the picture. What you do is you find a rising tower. Sometimes they have little Philippine straw hats over the top, and you'd go in the middle of a rapidly growing turret and put in a tiny bit of seeding agent. The cloud base gets bigger, and the part above the freezing level will double within a minute or two. Then the air down below is still rising, and it meets the stuff that's falling down, the bigger drops, and it starts a good rainstorm. Next, please. We took this apparatus to the Philippines, and the Air Force there was very kind and flew us around for months. This is a weather officer giving us a briefing. This is Ray Booker from a commercial cloud seeding outfit in And this is Captain Snopkowski and the rest of these gentlemen. I can't remember their names because they kept changing them. When they discovered what they could do, they kept changing the crews on us after a couple of days because they wanted to teach the whole Air Force how to do it. Next, please. We were using the C-130s and dropping the stuff from this little gadget here. Next, please. Here is a bunch of clouds that are starting to form over an island. None of them are very big. A few of them have reached the freezing level. So we seeded those. Next, please. And as soon as you began to release the heat of fusion, these clouds began to grow rapidly, and then they would suck in more air from underneath and the cloud would grow. And this cloud has had one seeding unit dropped in it. Next, please. The growth around the base of the cloud was absolutely remarkable. Next, please. The clouds in a uniform wind shear are not seeded the same way, because if you seed this part, it will just blow off the back. So what you do is you find a rapidly growing turret on the upwind side, and you seed that, and then a new one will start to form upwind, maybe a mile or two from the main cloud. So then you go get that one. Next, please. This is one of those clouds over Panay Island. It was leaning with the wind, and it was seated right here. And you can see that it started going straight up instead of sideways. And it rained out the back of the cloud, and pretty soon the whole island was covered. Next. Clouds of this sort, which are totally out of hand, can be extinguished by flying through the lower part where the air is going up at a great rate and seed that very heavily. That makes the air rise so fast that it sucks in drier air from the sides and the cloud pinches off. You can stop the rain from a well-developed cloud this way. And we were using that on our hurricane efforts when we had to quit it. Next, please. This is a cloud that's growing through a dry layer. There's a dry layer in here, and what you do is you seed the top of the cloud, and then you don't get much out of it. It rains a little through the bottom. But if you go at it very carefully and slowly, you can humidify this dry air layer and make the rest of the cloud go and rain. Next, please. This is a case of a dry layer. It's in here, and here it's coming up and spreading out at the top. The seeding of the clouds depended on your ability to interpret the wind flow within the cloud. And the other people who were trying to figure out how to seed clouds, by and large, didn't go to the trouble of riding in the airplane that was doing the seeding, and they couldn't tell what was going on. Our people here were only too happy to go riding in airplanes. Next, please. Show you how effective this can be. This is an island in in the Philippines, and you see these two little lakes here and that one. We flew through the top of it with the C-130, and they dropped 3 units into it, into the top part of the cloud, and we flew down below in a different airplane underneath it. Next, please. This is the same little cone of rain 20 minutes later. Next, please. This is a half an hour later. It really wet the whole place down. That was very impressive. And we could do it with great regularity. Next, please. It occurred to some of us watching the area where the rainfall had flooded the place that this might be a useful way of handling infantry. Of course, we had that figured out ahead of time, having been in the infantry during World War II. But this whole island was covered with about 40 miles on an edge from just a few of these units. Next, please. And more of the same. Next, please. Well, this is the end of the slides here. There's the airplane we were using to seed the clouds in the rain. You're always supposed to end the talks with a picture of a sunset, but the sun was obscured by the clouds in this day. We were faced with a couple of problems to begin with. We didn't have any meteorologists working here at the time, except the forecasters, and they weren't too busy to give us much attention. We didn't have a good theory for the growth of droplets, and that was developed by Dr. Gillespie from the University of Nevada, and our people, especially Dr. Gillespie, who is an expert on collisions, but that left us then with the problem of how to optimize the collisions. That was turned over in large part to Larry Matthews, whom I don't see him here today. He was a very brilliant physical chemist, and he solved this problem, and Gillespie solved the bigger problem of what happened between the collisions. And then we applied some of that to thermodynamics. And we could get the cloud growth, we could get the rate of removal of the water vapor and the release of energy. So we were on a sound theoretical basis. Now, we didn't have any meteorologists working at the time, just a bunch of physicists and chemists. So the meteorological people refused to publish any papers. We didn't meet their standards. So we formed the Weather Modification Association using a bunch of commercial operators who had been quick to pick up our stuff. And we formed this and then published our own little journal. And we had this group here had 10 publications in the first issue. But from then on, it was less trouble than we had had previously, because the guys had decided maybe we knew what we were talking about. The difficulty there and then became that the University of Chicago had a couple of years previously conducted what they regarded as a very carefully balanced statistical test. And they didn't produce anything. The trouble with their statistical test wasn't a test really. They never seeded clouds at all because they, instead of using pure silver iodide, which we did, they used a complex of silver iodide and sodium iodide, which dissolves rather quickly in the droplets, and so it doesn't introduce freezing. So Burkhardt sat down and worked out all of the theoretical balances for that type of reaction, and he published phase diagrams of how that went on. So with that information in hand, we knew we were doing the right things to get results. So the people at the University of Chicago claimed we were a bunch of fakes because they didn't do anything that worked. So I published a paper pointing out why the stuff dissolved in the water instead of starting the freezing. They haven't spoken to me since. So about that time, one of the people from the Secretary of Defense office was overseas, and he was bewildered by all of the monsoon, and he thought that maybe we could make the monsoon produce more water. So we got a telephone call late one night instructing us to be ready to go by the end of the week and start seeding clouds. So we went, and I remember loading the airplane. It was taking us over there on the airfield. So I said to the research department head, "Hey, you see, something does come of research." And he says, "That's not research." So I knew where we stood. It wasn't research, except on a much grander scale than they'd thought about previously. And again, the Weapons Center was the only place in the United States where we could have done mustered the kind of intelligence and kind of adventure spirit that we could here. So we went over there, and the Air Force had gotten into the act again, and they did all the seeding for us. Jack here was over there almost a year working on the problem. The rainfall was increased along the entire Ho Chi Minh Trail, so the people abandoned carrying supplies by truck because all the streams were flooded, and they had to carry the stuff by hand. So they had a lot of people, and they were quite eager to go ahead, and so they did that. And we had other people watching the trail, counting the number of folks walking along with packs, and we discovered that the traffic on the trail dropped to about a fourth of what it had been before. And then the monsoon quit, and so we quit until it started again. This went on for about 10 years, and we, in the meantime, had increased the ability to seed clouds. We figured out just how much material you needed which was about 1/100th of what we were using to begin with. So a few grams of silver iodide of the proper sizes and the proper purity were all that was needed. We didn't have much luck promoting this kind of work because it's theoretical work, and the policymakers and managers, most of them are incapable of understanding that kind of chicanery. So we kept at it anyway, and we kept moving the advances as fast as we could forward. So then about that time, this was now 1970, we were instructed to go to India and make it rain. And it didn't make it rain because there wasn't any there weren't no clouds, but we did get a few of them, and we succeeded in drenching those places. So then when we were on the way back from India, somebody else sent a message saying we should go to the Philippines. So we went, picked up all of our stuff and moved to the Philippine Air Base in Manila. We then worked the whole rest of the monsoon season, and we succeeded in wetting down every island in the archipelago repeatedly. The Filipinos were very happy about this. They hired a couple of cloud seeders and went on their own with it, using the materials we had developed here. In the meantime, we were having trouble with publication because the program had, once we began to work in Vietnam, it became classified top secret special access. And if you weren't on lists, you didn't get to participate. So we had a terrible time with the security arrangements, but we got that worked out. The worst of it was that the station commander hadn't been briefed, and it was kind of a difficult task convincing him that they must have had some good reason for not bringing him into it. That didn't make him very happy, but what we succeeded in doing was drawing so much attention to ourselves that the character who disclosed the Mai Tai massacre originally, I can't remember his name at the minute, found out about it, and he then made a big fuss in the papers and forced the publication of some of this stuff with the Pentagon papers. Well, we were regarded, when that happened, as being terrible warmongers, even though the war had been going on for 10 years. And it looked like we were bringing it to a halt. Yeah, okay. So about the same time, the environmentalists of the world had a big meeting in Copenhagen. And a Russian environmentalist who later turned out to be a colonel in the KGB was attending these meetings. And they knew all about what we were doing anyway, so that he exposed this whole thing to the people at these meetings, including a couple of Congress people, liberal Democrats, who decided that we should form a treaty with Russia and we would both quit this kind of nonsense. In the meantime, we'd been working with screening smoke, and we'd even found smokes that would obscure the flares. So we were quite pleased with ourselves. We were making great progress when this Russian environmentalist convinced these senators that we should have a treaty with Russia to quit this kind of nonsense forever. So it was formed, and the treaty was duly signed, and so we got put out of business. Well, the United States has a long history of telling the truth and abiding with what it says it's going to do. It quit the work completely, leaving a little bit still going with the commercial operators, and they shut down all the military applications, including us. The Russians shut it down to the point that they quit releasing the news about it, and they moved the whole thing to a 2-star general at a place called Nilchik. Nilchik very much resembles China Lake, and they kept on trying to rather unsuccessfully, I might say, to stop hail. Well, that is the end of our participation in it. So then we said, well, we got a bunch of good cloud physicists. Why don't we work on screening smoke some more? So somebody in the Pentagon heard about that, and they regarded screening smokes as geophysical warfare. So even though it had been shown by World War I that the casualty rates could be dropped by 100 by just furnishing good screening smoke, they wouldn't let us do it for ourselves, nor would they let us clear fog for runways if military aircraft were going to land or take off. We could do it for commercial aircraft, but not military. Now, we pay good money to keep these people in Congress, and I suppose I should be more respectful of them. But they annoyed me. And so that was the end of that. We'd had a program that lasted about a decade, was very successful, was fundamentally based on quite sound theory, and obscure theory at that. Nothing had been done with this theory since the mid-1800s, and we'd pushed it ahead into the mid-whatever they were. Anyway, we quit that, and then we had nothing else to do, and since management had made us stop everything else that we were working on except the weather, before the weather got shut off, then we had nothing really to do, and so the group broke up. The people like Jack are still here, and they're still doing their best, but it's nowhere near as much fun if you can't fly through it. Thanks.
Does anybody have any questions for Dr. St. Amand? Anybody? I want to thank him. From the technical library, we have a poster, the one that we have outside for him.
Oh, thank you.
And we have a certificate of appreciation for your support of the Knock Weapons Technical Library Storytelling Program. Have I Got a Story for You? Thank you for sharing stories on the cloud seeding and weather modification.
Well, thank you, ma'am.
Thank you so much.
I'm very pleased to see this sort of a meeting because it gives us a chance to tell the rest of the group what's going on. Otherwise, you'd never hear about it. And when I started the technical director seminar about 20 years ago, I had exactly this in mind, but I didn't think it was going to be as neatly done as you've done it.
Thank you.
Thank you.
Thank you so much.